So thank you everyone for attending. I'm Javier. I'm coming from TNO, from the Netherlands Organization for Applied Scientific Research, and we'll be talking today about work that's been done in a team of people that you'll be seeing it example by example about physics-based modeling and optimization of hybrid power plants. I would like to start mentioning a bit about TNO and system integration in general. So we are the Netherlands Organization for Applied Scientific Research, and we have several locations that you can see here that work in projects that are related to the topic of hydrogen combined with renewable energies. We have an energy and materials transition unit, and works in different parts from subsurface to transport, transition, supply, and demand. For example, the electrification and decarbonization of industry. We have quite a few projects that are working on that, and I would like to highlight three of them. The first one is the North Sea Energy Program, that with a set of partners that you can see here, where we look at different scenarios within the Dutch North Sea and see how they will develop in terms of their energy assets and infrastructure for 2040 and 2050. Then we also have Poseidon, where it's an offshore electrolyzer that is aiming to produce hydrogen to also be sent onshore, and one of the first of its kind. And another project that it's a Hy3 Plus, where we can look at the infrastructure in terms of hydrogen pipelines for the Netherlands, Germany, and Belgium. So many others. I leave as the presentation is being recorded. I thought I would leave here the names in case you are curious and want to take a look afterward. We zoom in a little bit on the activities that it's done within the team of people that I work with. So we work in energy system modeling, and that means that we take a look at different commodities and often commodities together. So the interactions between electricity, hydrogen, heat, CO2, and natural gas. We take a look sometimes from an infrastructure perspective, so the whole network, such as what you could see in the North Sea Energy Program here, where you have cables, pipelines, and also storage locations within the offshore system, and then you model each of these nodes to see what are the physical properties of each of them. But also we look at it on a more zoom-in version in an asset level, what we call an asset here, where you look at a specific part of that system. And that is mostly what this presentation would be about dynamic simulations, where we look at the combination of physics and techno-economics. Zooming in again, we mostly will be talking today about intermittency and system integration. So the motivation is quite clear in the sense that we have an increasing penetration of renewable energy, and that means that generally tends to be from intermittent sources such as offshore wind or solar, and dealing with flexibility becomes of paramount importance. We generally have in countries like the Netherlands with an industrial sector that usually demands something close to a flat demand of energy, and then we have a supply which has usually some degree of intermittency. So we look at different parts of the system, from the supply to infrastructure, utilities, process, and storage, to see where can we deal with that flexibility. So where that flexibility has the greatest added value, and how we can make a system that is resilient and is also fit for purpose. Then zooming in even more of what this presentation will be about in terms of the main knowledge area that we expect to do is something around here. So we wanted to give an explanation of the level of physical detail of the tools that we have. So we put here one graph that has been reconstructed of one of our papers, where we show many different tools that exist in literature for computations of energy assets and networks, and we divide that in two axes. One of them is the technology detail, so from linearized physics to possibly nonlinear 0D to up to 3D, and then the number of components. So you usually see a line like this, where the greatest amount of components and less physics that incorporate, and vice versa. And in our team, well, we saw that there was a gap or a perceived gap from our sense that was on this particular aspect, that was on the nonlinear modeling of multi-energy assets. So when we are combining different parts of the system, such as offshore wind, on solar, transport and storage, conversion to different chemicals. And we want to put these pieces together with intermittency, with market analysis, combining physics and techno-economics KPIs. And we decided to create our own tools for that. And that is what we will be talking about. So some examples in this presentation. We will be showing 3. So one of them is PyDolphin, where this graph is also coming from, that mostly goes into equation-based models and also machine learning models. We'll be talking mostly about equation-based in this presentation, but also we have a few mixed integer linear programming models that are more in the left side of this green area. So we cover different parts here today, and you will see 3 examples of each of them. I want to outline 3 different case studies where we use them and we found different added values for parts of the system. These ones will be mostly for asset owners, but it also includes synergies with other parties. The first one is comprised of an offshore wind park and a hydrogen production asset, and it's been done by my colleagues out here. So in our problem that we define here is that the Netherlands has a strategic ambition of increasing the offshore wind capacities much more than we have at the moment. So projections were in the order of 70 gigawatts in 2050. And if you look a map of the Dutch North Sea, or expected how the Dutch North Sea will look like, you see it's also a busy North Sea. We are a small country and we want to put many different assets. So that means that the complexity of building them is can be also high and challenging in some parts. There are also ambitions of having hydrogen production there. So with that, part of the offshore wind power, use it for offshore hydrogen production, and then transport it via pipelines to the landing points, up to 30 terawatt hour per year. But as offshore operations and maintenance can be complex and expensive, we were thinking if there were some way that we could operate it in such a way that we can minimize the degradation of the system. So we call it a smart power allocation, and we balance 2 different objectives. One of them is how much we produce, but the second one is the stack replacement costs. So we can minimize the amount of times that we need to go offshore. Sorry. All right. I cannot see anything. I can only hear. So that's all right. So we wanted to explore if we could do this model-based optimization to increase the profit and at the same time minimizing the stack replacement costs. So we zoom into part of this system that you see here, and you can have a schematic representation in here. So our methodology is that we will be using a system that is composed of wind and solar in our case. So we fix the sizes of them to 50 megawatts with n independently controllable electrolyzers. So in our case, we assume that we have a platform, and within that platform where the electrolyzer asset, you have n independent modules that you can operate each of them with their own power allocation. And for that, what we have is an MILP-based solver, the Synergia tool that we did, and we maximize an objective function with 2 terms. So we try to balance how much hydrogen we produce and how much revenue we obtain from it. And the second one is balancing with the stack replacement cost. So if we produce too much, but at the same time, we have too many costs because we have too much degradation, then our overall profit is lower. So we put some assumptions, such as a minimum load of the components and some physics incorporated into it, such as how the electrolyzer performs. And we use simulated data for the Dutch North Sea for the wind and solar power curves. So we have hourly profiles, and that's also in the other examples of the presentation of the wind and solar in our cases, and we assume a certain amount of revenue for hydrogen. For all the examples here, whenever revenue is there, we don't make any distinction regarding if that is an actual market value, if that comes with any subsidies, with any premiums for low carbon hydrogen. We just assume that revenue goes there for the asset owner. These are the results that we obtain. So we were taking a look and see what happens if we can control only one electrolyzer independent, or let's say all the modules go at the same time, or if we have a higher number of independently controllable units. And what you see is that by using this higher number of electrolyzers and balancing their power allocation, we have a little bit of more of hydrogen produced that is extra, that comes associated with the lower degradation overall. But secondly, and what is most important in our case, is that the number of shutdowns is reduced significantly. So in our case, you see 25%, a little bit more than 25% less shutdowns compared to the baseline case. And that is quite relevant because the system profit that you see here, it does incorporate the cost of stack replacement, but it does not include non-financial contributions. For example, the operational complexity that comes associated with having more shutdowns. And particularly in a busy environment like the Dutch North Sea, and minimizing this is quite relevant. You may not have the vessel availability whenever you want to. It may take some time due to the whole procedure within the value chain. So this 25% shutdowns with also a modest increase of the profit was a very nice result in our case. Then, by the way, if you have any questions, as we have different examples, and you want to also go not at the end of the presentation, but already make something, feel free to do so. Otherwise, I'll keep going. Rafael?
Yeah, nice. I just wanted to ask about how did you incorporate degradation in the IEA, the linear optimization framework? Because degradation is non-linear. So how did you manage? Did you just made a penalty for the shutdowns and did not updated the efficiency of the electrolyzer, or did you did something fancy?
Yeah, so this is a relatively simplified example that I'm showing here for two reasons. So we do have performance penalties for both operating hours and also shutdowns, each of them with their own contributions. And that is it. But as you say, it's a very non-linear process, and many unknowns are there also of how that would be in offshore conditions as well. So this is the first step towards saying, would that make sense to explore further? So we can in the future incorporate more complex expressions for how the degradation performs, and then update also the MIOP-based model with it.
All right.
Does that answer your question?
Yep. Yep.
Great. All right. If no more questions are for now, then I'll go to the second example. Now we change from offshore to onshore and from wind to solar, despite what the background here shows on the little wind, but this is the image that I found. So in our case, we are going to go to a very different area that is the effect of the grid tariffs for our asset. And problems, I mentioned before that the Dutch North Sea is busy, but also the Dutch inland is busy as well. So you see here on the map on the right, coming from Nijmegen, Netherlands, that several areas of the Netherlands are reaching their limits in both the transmission and the distribution grids. So they are reaching their capacity limits, and the congestion is expected to be quite high if nothing changes. That means that there's a high amount of work that is put in grid reinforcement, but grid reinforcement is expensive. So it can be in the order of billions of euros of investment by the different DSOs combined per year. And it's not only the economic aspect of it, but as we also mentioned before, it's also the non-financial aspects of it are relevant. For example, shortage of workers, raw materials, provision authorization. So apart from the cost, it may take longer than the initial projections once you consider the different factors. So we would ask if it would be possible to take a look and see if there were synergies between the distribution system operator and the asset owner, an asset owner that contains an electrolyzer, to try to see if we could help to the grid congestion relief and at the same time improving the business case of the asset owner itself. So ideally, the question would be if you are able to put an electrolyzer in specific areas that are less congested, and that also gets incentivized by certain contract mechanisms, then you fulfill both the benefit of the DSO and the benefit for the asset owner. For that, we look at a system like this. This is our solar park that was 150 megawatt peak, and then with a small electrolyzer compared to the previous one, and that gets then transported with hydrogen produced via trucks to the stations. So this asset is inspired by an existing project that is H2 Hollandia that is in the northeast part of the Netherlands. What we are doing here is with a physics-based solver, the TNO SpyDolphin 2, that contains a nonlinear representation of the performance of the electrolyzer and also constraints on it. We are modeling how it behaves on an hourly basis. For that, we use also synthetic market data, simulating one scenario for 2030. So one of the potential views of how the world will look like in 2030 by the TNO SI2. And what we are looking is at the difference on the levelized cost of hydrogen for different configurations. We are going to test 3 of them. One of them would be the asset itself without a grid connection. So basically, when we have solar, we send to the electrolyzer preferably, and otherwise that goes to the grid. When there's no solar, then we need to shut down the electrolyzer. Then the second configuration comes with a grid connection and a typical contract. And the third one is with a grid connection and the new contract that we are proposing in this case. And we also make a distinction in this particular project because we only purchase power from the grid if the market price fulfills the EU conditions. So we can consider the hydrogen as a renewable fuel of non-biological origin. So what that means is that we only purchase from the grid if, roughly speaking, the grid is low carbon intensity, as the price strongly correlates with the carbon intensity of the grid. So we use the EU delegated acts for that. In that way, whatever hydrogen that we are putting here can be labeled as a renewable fuel of non-biological origin, and that comes also associated with potential premiums, subsidies, and other components that increase its value. The define the grid tariffs, we took a look at what is the, Italo Roberto, you have a question?
Yes, please. Could you go back to the previous slide? Yes.
Excuse me, I hear it very faintly. I cannot hear it very loud.
Now?
Yeah, now it's great. Thanks.
I see in this graphic the 60 megavolt amperes. That is the amount of power that you are considering to transfer to the grid from the PV system.
Indeed, that is how it was. It was in the project that we took as a reference. So there was a certain degree of curtailment associated with that. But that is also because in the Netherlands, the load factor of the solar is quite low. So you also reach the peak hours quite in not many instances.
Okay, because that was my concern. Let's say that if you have a full power of the PV system and you have the capacity of transfer just 60 megavolt ampere, what about the other 55 megawatt?
Yeah, indeed.
5 megawatts you have there, 50 megawatt. Well, that's.
Yeah, it is how it was defined. So we are not the asset owner of this. We took the project as a reference, and the reasoning that we got from this was precisely that curtailment does happen in certain time steps. And that is accepted. On the other hand, you will have higher costs on the infrastructure that also have also cost some money. We need to have, so they balance all the elements and they decide on this. In our case, we just simply take in our system. But also to add to that, in our case, the main metric that I will be showing is the levelized cost of hydrogen of this part of the system. So whatever results you see don't come with any revenues associated with the solar power sold, because it's levelized cost, but nothing that talks about revenues. So it does not affect our calculations. I hope that's clear.
Okay, thank you.
Welcome. Right. Another question?
I think you're gonna get eventually, but then how do you separate this? Because how do you separate the revenues from the solar? Because you said that it's levelized cost, but I'm puzzled a little bit. How did you manage to separate?
Yeah, indeed. So what we did was basically establishing how much. So we considered the system, you could say, of this part. You can see my cursor, no? My
Yes.
the the red light. Sorry, English is not my first language. Yeah, so we considered this part of the system, and what we did, we had the same doubt as you, is saying how do we consider the energy that we are getting from solar, because we are getting it not for free, because building the system costs money. So in our case, we assume that whenever we got energy from the solar system, it would be at the cost or at the same cost or at the same value that would be the market rate of the day ahead market in that particular hour. So if we could have sold without thinking about curtailment, only if we could have sold this solar power at 60 euro megawatt hour, for saying something, that is the cost of the electricity that comes for the electrolyzer.
All right, I get it.
Right. Now we get into the grid tariffs. We were looking at the distribution grid in our case, and we took a look at how the different parts of the tariffs for the distribution system operators are in the Netherlands. And you have costs like this, and you have one-time cost for being able to connect to the grid. Then you have annual costs that are associated with a periodic connection fee, and then the monthly transport rates. We did this project in collaboration with different distribution system operators, and in the conversation with them, it came that these two particular components were two that we could modify in order to build this new type of contract. But we only focus on this. The other parts are fixed ones and don't change. And we thought, okay, can we then synergize these aspects by putting a reduction in these components in exchange for restricting your grid consumption in certain periods? And to do that, we have a graph that looks like this. We have a grid tariff reduction table where this is basically the number of how much your tariff here will be scaled with. So if you consume power in the green areas that you see here, then you have a 30% reduction on your tariff. And if you decide to consume power in the areas that are red, then you pay the full tariff. And not only that, but because those are the potentially congested times, then your contract tells you that you can be restricted 15% of the time in the red area. So you may be asked to consume, but you may not be allowed to. So those are the two things that balance it. And we wanted to know if the business case will be better or worse, because you do consume less electricity, which means you produce less hydrogen, but at the same time, you have a discount on your grid tariff. So we look at which of the two elements was stronger with the current data that we have at the moment, and those were our tests. We put two different types of firm tariffs, but there are more, and they're also in the report that is also linked in the slide before. But we will show two of them, where for these two numbers, one of them we take the average monthly consumption, and in the other we completely eliminate one of the two to see basically what would be the upper limit of the discounts that you could get. And these are the results. So looking first at the grid tariff component by itself, what we see is that with the non-firm tariffs, we have a strong reduction of that cost. And that was to be expected because, of course, we have those two components that get smaller. But the interesting part came when you compare the no grid versus firm, non-firm, and non-firm 1 and 2. When we compare the cases of no grid versus the normal grid tariff, then we see that the levelized cost of hydrogen of our system are roughly the same. So up to the uncertainty of our calculations. And that comes because your grid tariff that you can see here it's basically compensated by the extra hydrogen that you are producing. But when we have the non-firm tariffs and we play with the table here, did achieve a reduction in the levelized cost of hydrogen, 0.3 euro per kilo, and it's a modest reduction, but also a consistent reduction in the different cases that we did. Here, as you see in the two tariffs, it comes associated with the non-financial part that we cannot consider in our current model. That is that grid congestion relief, because we are not consuming in parts of that red area. Then we are not affecting that grid congestion as much, and at the same time we have slightly better business case. So this is a good example of synergies that you can make when DSOs talk with asset owners. And the continuation of this is really saying if there can be other type of formulations that could help even further in heavily congested areas. All right. Now if there are no questions, then I'll go for the last area, for the last example. That is about revenue streams in this case. So diversifying these revenue streams with multiple markets and ancillary services. So in our case, what we are seeing is that there's a challenging business case of certain offshore assets that comes due to cost, future market expectations, uncertainties. So one of the aspects that is being explored, particularly with more and more storage solutions coming into play, is hybrid power plants that have different degrees of flexibility to diversify the revenue streams. So when we have supply-demand mismatch, forecasting errors, different balancing markets, ancillary services, all of those aspects may be relevant for us to participate as a hybrid power plant in this. And we were exploring if this revenue stacking may be able to increase the overall profitability of a project. And that also gets balanced with operational complexity. So what we were taking a look at is at the optimal size and configuration of a hybrid power plant across multiple markets and under physical constraints. That was the second aspect that was relevant or innovative this particular study. And methodology looks like this. This is from a paper submitted that's still on the review process. It's not published yet, but you can see the original sources of the tools here. We have a combination of models. We have a physics-based model, PyDolphin. You've heard from the previous project that are non-linear models, but also we have an MILP model before that. So what we do is that we have for a whole year wind power, PV, and markets, and we can enter with that information into our models. And the first thing is that we have this MILP model that looks for 24 hours and tells us how we should be bidding in the different markets in order to maximize our profit for those 24 hours. And that from those set points, we give them to the nonlinear models to see if those set points are actually physically feasible. So what we will do is that we correct those set points based on the physical constraints on the system. So we will not have a fully optimum solution, but we are hopefully close enough. And we do this every 24 hours until we reach a whole year of operation. And that is also nested with a sizing optimization routine in such a way that we can take a look at different parts of the system and have this operation and sizing together. One aspect that is relevant to mention is that we didn't put any forecasting uncertainties incorporated here. So these are also upper case limits of what you can achieve, because if we have forecasting errors incorporated here, your bidding would also get affected by that. So this is the first step in the academic research. Our asset looks like this. So in our case, we have wind, solar, hydrogen, and battery, all of that offshore. And in our case, we also put the grid tariffs that are incorporated in it. No, in this case, no different contracts, only our firm contracts. This at the transmission level as well. And we have different markets. We have hydrogen that is a fixed price, and then day ahead that goes every hour, and two services that are the frequency restoration reserve for, so we have the reservation and the activation, and those two go every 15 minutes. So we have dual time scales for this, and we also need to do something about it. So as I mentioned before, we have the linear models and the nonlinear models. So the way that we do it is that we first aim to do a set point with the linear models, and in the corrections, then we need to decide which market should we compromise in case we cannot sell or we cannot buy due to physical constraints. So in our case, we decided to enforce these ones while correcting with our day ahead bidding. You could also make more complex strategies, looking at every time step what would be the optimal strategy. But in our case, well, this is the first approximation that we made. So you can see also a schematic representation here on the right of how it looks like for the hybrid power plant when you have simply the day ahead market. So you have a certain minimum load that you cannot access, and then this is the part that you have for day ahead. And in our case, we have a certain reserve capacity for if you go to the reservation AFRR, or you can also have fully day ahead or fully AFRR activation, or other combinations that you can think of. And the results are like this. So you can see single market on the top, a multi-market on the bottom. So what we see with the multi-market is that, again, we have a modest increase in profit, but also consistent across the different cases. So we see in this case a 5% extra profit when we go to the multiple markets. And something that is not in these plots is that the optimum sizing for the electrolyzer was also larger. So it went to around 300 megawatt compared to 250 megawatt. So that also results in a greater revenue of the hydrogen. And we can also see that the electrolyzer can be used as a flexibility absorbing asset for AFRR services, as you can ramp up, ramp down fast enough on these 15 minutes time scales. But one aspect that we already highlighted in the project before, and that we also see here, is that the grid tariffs play a significant role in limiting the further profit. So when you look at the tariffs here, compared to the different revenues that are obtained in the markets, you see that they almost cancel out. So you do have extra revenues on hydrogen, and that drives the higher profit overall, but the component of the grid tariffs is quite relevant in our cases. So this is something to be monitored in case we are going to have assets that heavily consume from the grid, and the grid tariffs become different in the future, as the result between single and multiple market may be different in that case. All right. So then we get to the last slide about conclusions. We have shown 3 examples of how we try to find synergies between different parts of the assets of power and hydrogen, and also between asset owners and DSOs in our case, but we also do it for other examples. And I like to put on the right other areas of active research that are related to other projects that we are doing at the moment, and are also combined with the tools that you've seen before. So this includes, we've shown a little bit about the gradation and modeling, the revenue stacking, but also other areas that we then show comes from forecasting, machine learning modeling, and other parts of stronger coordination between multiple asset owners or other stakeholders. There was a question, I think I've seen a hand. A question? I cannot see anything.
I think the hand was lowered, so you can go ahead and finish up.
Then no problem. So yeah, this concludes the presentation so far. And let me know if you have any questions, if you want any further information or sources for any of this project.